Hey statisticians, I'm going to talk really fast. Hopefully you'll be able to get these down so that you can get off to night-night land. All right, so chapter 7 is going to build off of our knowledge about probability from chapter 6, and it's talking about random variables, which will always be a capital letter. Typically, we'll be looking at capital X and capital Y, but they could use some other capital letter. And it represents a possible set of outcomes. And by that, I've provided you a couple of examples. So let's say X is the sum of two dice. Well, we know that all the outcomes, when we looked at the two dice table where we were doing sums back in your chapter 6 notes, the possible outcomes were everywhere from 2, 3, 4, all the way up to 12. So random variable X could have that set of outcomes if it was the sum of two dice. If I look at the number of heads and 3 coin flips, we actually made the tree diagram for this, and it was possible that I had no heads, in other words, they all came up tails, or I could have 1 heads, or 2 heads, or 3 heads. So random variable Y would be that set. So now, if I look at the probability distribution for X, easy for me to say, I would start by listing first all of the outcomes for X, and I'm going to have to list each one individually. And then you're going to need to go back and look at that table alongside this so you know where I got these numbers. But in that table there was only 1 2 that showed up, so the probability of a 2 happening was 1 out of 36. However, there was 2 3s, so their probability was 2 out of 36. There was 3 4s in my table. There was 4 5s, so 4 out of 36. I don't know where that came from. There was 5 6s, so out of the entire table, 536. There was 6 7s, and then it started going back down, so there was only 8. There was 5 8s, there was 4 9s, there were 3 10s, 2 11s, and 1 12. And if I add all these probabilities up, just to make sure that this is a legitimate probability distribution, I do in fact get 1. And it must total 1 for the entire sample space, as we learned back in chapter 6. And then if you go back and look in your notes where we made the tree diagram for the coin flipping 3 times, I've listed all the outcomes again over here to the right. And if I'm keeping track of heads, the probability that I get 0 heads is 1 out of those 8 outcomes. That's right there. The probability that I get 1 head is 3 out of the 8 outcomes. So there was 1 there, there was 1 here, there was 1 here. The probability that I get 2 heads, well, I just count them up. So that's also 3 8s. And the probability that I get 3 heads was only this first one, is 1 out of 8. And again, if I want to make sure it's a legitimate probability distribution, I double check and make sure that it does in fact, the probabilities all add up to 1, the entire sample space. So now, discrete random variable versus continuous random variable. Discrete random variables are countable, or we could say they're integral. In other words, they're integers. So I can't have 2.5. And so examples might be of discrete random variables would be the number of pets, or the number of cars, or the number of siblings. Although, you know, we might debate whether our sibling is a full mental faculty or not. But you do in fact have a whole sibling if you have one. Versus continuous random variable, it just falls on an interval. And so some examples of that, boy, I'm struggling with the talking tonight, is things like weight or time. Because I can have things like decimals or halves. Temperature would be another one.